Hello everyone, let's take a look at our next problem. So this question is very similar to the previous one, where we have 3 points A, B, and C on a parabola y equals x squared, with 1 point B at the origin, and we want the triangle formed by A, B, and C to be similar to a 3, 4, 5 triangle. Okay, so this time we will have 2 degrees of freedom. We can move point A to the left and point B to the right, or point C to the right, but they don't have to move left and right the same distances. The first, and what's coming to my mind immediately is we want things to be similar to a particular right triangle, and so we're probably going to, maybe we want to work with the angles between the points on the curve here this time. So here's the point B. Again, we'll say that the point A is to the left and the point C is to the right. And you know, I'm starting to think that maybe, you know, the point B doesn't necessarily have to be the one that's a right angle. Maybe it is. Maybe the other, maybe point A or point C is the one that has the right angle. What can we do here? Well, again, everything is going to be determined by the horizontal coordinate of x, of the points A and C. So we'll call those XA and XC. So this means, of course, that the point A lies at XA squared, and C lies at XC and XC squared. I'm going to see what happens when I just arbitrarily say that the point B is the right angle. So we're going to suppose that the right angle is at B. And this should give us a relation between XA and XC, because, you know, if we think of BC as a vector and BA as a vector, then the dot product between them will be 0. So BA dot BC is equal to 0. Because the point B is the origin, then, you know, the coordinates of these vectors are really just the coordinates of these points. So this means that XA, XC plus XA squared, XC squared is equal to 0. And, you know, we'll assume that XA and XC are themselves not equal to 0. And so I can factor out an XA times XC from both sides of this, right? So I'll write this like the following. Okay, so then, you know, I can cancel that from both sides. I'm assuming both of these are non-zero. And so this tells me that XA is equal to -1 divided by XC. Okay, so now I in fact have only 1 degree of freedom. As soon as I choose XA, I get XC, or vice versa. What I'll do is I'll let XC be my free parameter here. Okay, so XA is equal to -1 over XC. And what I need to do now is I need one more condition. I need one more condition to make it so that I actually have the lengths of each side of this triangle in the right ratio. So what I'm going to do is I'm going to write down the ratio between the length of BC and BA. So what I should have is I need the length of BC divided by the length of BA. This should be equal to 3 over 4 or 4 over 3, right? We need ABC to be similar to a 3, 4, 5 triangle. I'm sort of assuming here now that BC is the side corresponding to 3 and BA is the side corresponding to 4. But this kind of, my intuition now is telling me this will sort of take care of both answers. I'll just have to reverse the coordinates. This will give me one solution, and then when I take the reciprocal of this, that'll give me the other solution. But that would also sort of, it's taken care of by the symmetry between XA and XC here. Okay, so let's write out what BC is, the length BC. Well, this will be XC squared plus XC to the 4 under square root. In fact, I'll just write BC squared here, which by our convention, we're setting XC equal to X. This is X squared plus X to the 4. And the length BA squared is XA squared plus XA to the 4, which is one over X squared plus 1 over X to the 4. Okay, so writing out this ratio now, I have X squared plus X to the 4 divided by 1 over, let's use negative exponents here, X to the negative 2 plus X to the negative 4 is equal to 9 over 16. This looks like it's getting messy. 16x squared plus 16x to the 4 is equal to 9x to the negative 2 plus 9x to the negative 4. Oh, wow. Okay, I'm going to multiply through by x to the 4 and see what happens. This looks very ugly. So, I see that this is a quartic equation with respect to x squared. Well, in fact, if we replace everything with, this parabola is given by y equals x squared. So if we just think about using the y coordinates of everything instead of the x coordinates, this is the same as 16y to the 4 plus 16y to the 6 minus 9y minus 9 equals 0. Does this even have a solution? If I write this as equals 9, so when y is equal to 0, the left-hand side is 0, and when y is very large, the left-hand side is also very large. So this definitely has at least one solution for y. I'm not about to look up the quartic equation or quartic formula and solve for y here. Oh, this should be a y cubed. Wait, yeah, y cubed. Is it possible? Let me just make sure that I got these distances correct. So BC, x squared plus x to the 4. 1 over x squared plus 1 over x to the 4. So this definitely has at least one positive root for y. Okay, and that will give us, that'll give us one of the solutions. That'll give us the solution where BC over BA is 3 over 4. And this all assumed that this is all assuming that the right angle is at the point B. So I'm not sure how much farther we can take things from here. Okay, so okay, so positive root will give us one solution. So the positive root of this will give us one solution, and then of course we can just reflect everything through the y-axis. So basically, just kind of like swap A and C, and that'll give us another solution. Let's assume now that the right angle is at the point C. Okay, so we're just going to write down again a relationship between XA and XC, assuming that this right angle is at C. Okay, so what does this mean? This means that CA dot CB is equal to 0, where CA is equal to XA minus XC, XA squared minus XC squared, and CB is equal to negative XC squared. Okay, so the dot product is XA minus XC multiplied by negative XC plus XA squared minus XC squared times negative XC squared. Okay, and this has to equal 0. So I have XA, I'll cancel out negative signs everywhere, XA XC minus XC squared plus XA squared XC squared minus XC to the 4 is equal to 0. I can cancel an XC everywhere. This doesn't, I mean, if I think of this as a quadratic equation in terms of XA, then I have XA in terms of XC. So let me just write this in a form which you might recognize. Okay, so by the quadratic formula, I feel like something is a little off here. There's sort of like a unit. Units aren't really working out here. What's going on? Where did I make my mistake? It's the vector CA. This is the vector CB. It's the dot product. Yeah. Should be equal to 0. XA, XC, XC squared. XA squared, XC squared. XC to the 4. Cancel an XC everywhere. Yeah, I guess we can expect there to be a unit mismatch because the vertical coordinate is measured in units that are the square of the horizontal coordinate. So things are a little bit funky in that regard. Okay, so I have a relationship between XA and XC. I'm of course taking, XC I'm assuming is positive. Do I need to assume XC is positive? I guess I don't, right? This will be positive. The signs should just sort of work out here, right? It shouldn't matter whether I assume XC is positive or negative, but the choice of the plus or minus here is probably going to also correspond to the symmetry we had before, where we can swap, we can like reflect A and C through the y-axis. Okay, anyway. So I have XA in terms of XC, assuming the right angle is at C, and then I would want to write down again, well, now things are, if I assume the right angle is here at C, I mean, let me redraw this so it makes more sense. If the right angle is there, try and make it at least somewhat to scale. Okay, well, it's obviously going way off in the distance up there. Ooh. So this is the point. This was supposed to be a right angle. It doesn't look like a right angle at all. I wonder if, yeah, any straight line emanating from here will intersect the other part of the parabola. So that's C. This thing is going way out in that direction. So, the question is, which of these two sides here do I associate with the 3 or 4 value of the 3, 4, 5 triangle? This is the hypotenuse out here, so that has to be the one that corresponds to the side length of 5. But I would have to write something like CA divided by CB is equal to 3 over 4 or 4 over 3, just like I did before. And then write out CA and CB, these lengths, in terms of XC. And then solve for XC. This seems like it's going to be a bit of a mess. So I wonder if there's some kind of simplification we can make. I don't see it immediately. I'm not sure. And it's possible also that, God, it would not shock me at all that one of these two fractions won't have a solution. That's I'm not certain about that, but just based on the, looking at the geometry here, well, no, I don't. I'm not sure. Not really sure, but yeah, this is kind of disgusting. This is not going to work out nicely at all. Maybe I can have a think about this one and return to it if I have any enlightening ideas. But for now, things are looking pretty messy. Even the previous version, even the previous sort of slightly less messy case, we couldn't write things in closed form. So I'm not sure.